So now we're going to use the separating hyperplane theorem to prove Farka's lemma. A refresher of the separating hyperplane theorem. So if x transpose y star is alpha, then x transpose y is less than or equal to alpha, and alpha is less than x transpose b. So we have the hierarchy is x transpose y could be less than or equal to alpha, but alpha is less than x transpose b. So we haven't proved this yet, but let's say that A is an m by n matrix, and vector b is has dimension n. Exactly one of the following two systems has a solution: either the primal condition or the what's it called again? The primal and dual conditions. So one is primal, two is dual. There exists vector lambda such that a lambda is equal to b. That's the cone where lambda is greater than or equal to 0. Yeah, that's the cone. Or there exists vector x such that a transpose x is less than or equal to 0 and x transpose b is greater than 0. So those are the two things that we're going to consider. A proof of Farka's lemma. So let C be the cone, be defined as the set of all a lambda such that lambda is greater than or equal to 0. That is for all lambdas, which is a subset of Rn, or vectors of length n. We can prove C is convex using the definition of convexity. So I'll leave that as an exercise. So now let's suppose that B is not a member of C. That is that the primal condition is not true. So if the primal condition isn't true, that is, if B is not a member of the cone C, then by the separating hyperplane theorem, x transpose times this vector B is greater than some scalar alpha. And x transpose times a vector in the cone, we'll call it y, is equal to a lambda, is a member of C, the cone, is less than or equal to alpha. And because it's in the cone, a lambda, lambda must be greater than or equal to 0. That is, all components of this lambda vector are greater than or equal to 0. So let's just say that we have a beta greater than 0. And then we can express some, the y vector as beta times some vector c. So we have x transpose times that is equal to beta x transpose c, and that's less than or equal to alpha. Since beta is greater than 0, that must be true. Then if we divide by beta, we get x transpose c is less than or equal to alpha divided by beta. So now here's the interesting part. We know that c actually is in the cone. Well, why is that? It's because c is y divided by beta. Beta is greater than 0. So 1 over beta is a scaling factor. So it's y times 1 over beta. So y times something greater than 0. Y is equal to a lambda. So basically, we're multiplying lambda by that's 1 over beta, where 1 over beta is greater than 0. Therefore, it'll still be greater than or equal to 0, the vector components. So that means that C is still a member of the cone. So we have this limit on X transpose C, where C is a vector in the cone. But how far can we go? What is the minimum value such that the X transpose C can be? So what is that minimum alpha over beta? Well, we can get that minimum by making beta approach infinity. And that means that alpha over beta approaches 0. But not only that, but C can be the vector 0. So the minimum X transpose C is 0. So that minimum, we can call it gamma, that minimum factor must be 0 in the separating hyperplane theorem. In the previous slide, we called it that factor alpha, so I guess we'll say alpha. We'll set that to equal to 0. So this must be true by the separating hyperplane theorem, where y is just a vector in the cone, and b is a vector that's not in the cone. All right, so now we can go a step further. If we take X transpose Y as less than or equal to 0, for all Y is a member of the cone, then if we follow this line, we see that Y must be equal to A lambda, where the components of lambda are greater than or equal to 0. And this must be less than or equal to 0, as we've figured out previously. So we know that we can kind of get rid of these parentheses algebraically. And if we have X transpose A, we can make some parentheses around those, transpose it. So the inside we can transpose. The transpose of a transpose is just X transpose A. And if we transpose it, then we reverse the order and transpose each component within the parentheses. So we got A transpose X transpose times lambda is less than or equal to 0. So these two statements are equivalent, this one and this one. So here's the hard part. This implies that A transpose times X is less than or equal to 0. Now, why is that true? Why is this less than or equal to 0? It has to be less than or equal to 0, actually. Well, because you can imagine that if one element of A transpose X, that vector, were positive, right? Let's just say that one of those elements were positive, then a large enough lambda can make this thing over here, this whole expression, positive. But you want it to be less than or equal to 0. So that means that this has to be, well, all of its components have to be less than or equal to 0 if you want to be satisfied for all lambda whose components are greater than or equal to 0. So yeah, that's the explanation. Hopefully that makes sense. All right, so great. We have recovered the dual condition because we said the primal condition isn't true, so that means the dual condition must be true. We proved that. But what about the dual condition? What if that's false? Well, then the primal condition must be true. Well, why is that? Well, because dual condition is false implies that B is a member of C, right? That implies that B is a member of C. And B is a member of C implies that, well, the primal condition is true. So if B is not a member of C, that is if 2 is false, or the dual condition is false, then B must be a member of C. That is that 1 or the primal condition must be true. So we proved both ways, and that is the proof for Farka's lemma. Next, we'll be proving the Fritz-John conditions. That is the next video.